All right, we're going to look at Chapter 7 quiz. I apologize for not being able to get to it in class, but with classes going from an hour down to 40 minutes, we lose a lot. So we'll just talk through some of these problems. If you have questions after we do this, just email me, or send me a message on Remind or whatever. Parameter in the statistic, in the situation, the parameter is 40% of the people who, or of the residents who would say answer yes. So it's really just 40%. It's just the number. The statistic is a proportion of 100 people from the random sample. A lot of us forgot or did not put 100 people. I want you to put the sample size in there so it's more specific. Letter B was not as successful. It describes the distribution of the proportion. Some of you didn't even have proportion in your answer. It describes the proportion of people who would answer yes in all possible samples of size 100 from the population. Or you could say from the same sample size or same population size or whatever it might be. Right? Look at this carefully and make sure that you understand all the nuances of what's going on there. The sampling distribution is a graph, or all the values that the statistic can take in any kind of sample of size 100 from our population. So it's finding the average or the mean of all the proportions. Letter C, we were good at. Letter D, good, but some of us did not talk about the 10% condition, because if our number is too big and it doesn't meet the 10% rule, we can't do it, or it wouldn't be different. Yeah, and we did E pretty well. Number 2 looked very good. Use, those of us who had some trouble, use the spread and the mean to differentiate these different answers. Overall, pretty good. Number 3, most of us, if not all of us, forgot the 10% rule yet again. You cannot find mean and standard deviation unless you apply the 10% rule. So, 10% rule first, then you can get the mean, then you can get the standard deviation. And after that, I guess you would do, in this case with proportions, the tens, then you have approximately normal sampling distribution of the proportion. That's kind of what we did. So 10% rule, clearly 60 rolls of a fair-sided, or 60 rolls of a die is less than 10% of all rolls of dice, or all die. All right, anyways, you get the idea. So describe the shape of the sample distribution for letter C here. And we just use our tens rule. 10%, but tens. And you need to keep going. Do not stop at this point. That tells me nothing. That tells me you can write numbers down. It doesn't tell me you can do any calculations. We want this. Don't give me work to do when I'm grading your paper. And when we talk about the sample distribution being normal, we want to say approximately. It's not exactly normal, but it's pretty darn close. Letter D was not as successful for some of us. We wanted to find the probability that the p-hat was greater than 0.5. So we've already done the 10% rule, done the 10, so we know we can find the standard deviation and the mean. We know it's approximately normal, so we can do our calculations. So the work that I want to see is in this box. Probability of p hat greater than 0.5 is 0.00310. Depending on how you rounded your standard deviation, it could be smaller. A lot of us have 0.002 something, and that's fine. We need the distribution drawn out with the mean labeled, the value that we're trying to find, the shading, and the standard deviation there. So it gives all the information. And then since the probability of getting p hat equals 0.5 when the mean is 1/3 is 0.003103, which is very low, we're suspicious about whether the die is fair. It's not very likely that we get a p hat of 0.5 when the mean is 1/3. So that's what we're talking about there. If we have some questions on that, we can discuss that a little bit more. Number 4a, pretty good. That is just x over n, where x is the number of successes over the sample size. Do not round it to 60%. Don't just chop off 0.8%. That's not good statistics. Give me the best approximation you can give without rounding. Letter B, we want to find the probability that the proportion in random sample of 2,500 adults is as far from 0.60 above or below as the results of this survey. So, 6 or 0.608 compared to 0.6 is, or 60 or 600 or whatever, 0.008. Now it's kind of small. Let's zoom in a little bit. So the upper bound is going to be, well, I guess there's two boundaries, 0.608. That's what most of us found. They also want below. So we go 0.008 below. 0.60 minus 0.008 is 0.592. And we want the area to the left there. Now, since they're the same distance away from the mean, the area is going to be the same in each tail. So first we do our 10% rule. Clearly 2,500 adults is less than 10% of all U.S. adults. We do our tens rule. N times p is greater than 10, n times 1 minus p greater than 10. Again, you need to get to this point. Do not make me do math. And we want to say we're approximately normal. So now we can find the mean, which is 0.60, standard deviation, which is, where is it? Oh, 0.009798. A lot of us got that one fine. So when you write this out, again, here is our work. This is what I want to see. Shaded graph, mean, the values, standard deviation, and the probability of the proportion p hat to be greater than or equal to 0.608. Multiplied by 2 because there are two sections that we're adding together, and they're both the same. They're symmetrical. So that's why a lot of us missed our answer there. We had half of 0.4142. But be careful. You got to read above or below. You could also find the area in between 0.592 and 0.608 and then subtract that from 1. I don't know which way is easier. Multiplying by 2 doesn't seem too difficult. Number 5, we're talking about newborn children, where we have a mean of 7.5 pounds, standard deviation of 1.25 pounds, and the government classifies a newborn as having low birth weight if it's less than 5.5 pounds. Or probably that a baby chosen at random weighs less than 5.5 pounds. This is not a sampling distribution. This is just a regular population distribution. So again, we have our distribution chart or graph. We draw that. Oops. Anything? We have our median, our mean marked, our value that we're finding, we have our standard deviation up here, which is exactly 1.25. It's not a sample, so it doesn't change. Then we want the probability of x being less than or equal to 5.5, which is that. And a lot of us did pretty well on that question. I'm not too concerned about that. When we get down to letter B, it's basically the same problem, except we're looking at x bar. That means we're looking at standard deviation of x bar is the standard deviation of the population divided by the square root of the sample size. So that's 100 or 1.25 for the original standard deviation divided by 3 for the sample size, not a whole lot. And the standard deviation changes a little bit, 0.7217. So we use that now, we do the same calculations in the calculator. But, again, the differences are, one has a bar, one doesn't. Scribble it out on top one here, 5A. That should not have the bar. B should, because we're talking about sampling distribution. Excuse me. We want to see distribution like that. And then let's letter C. Give me a second to get my pen that I want. Let's do pink. Anyway, explain why the probabilities in A and B are not equal. Well, 1 is the probability that one baby is less than 5.5 pounds. That's not as unlikely because there are small babies all the time. And it's just 1. Chance that we get one baby less than 5.5, it's going to happen. Actually, that's one of my daughters, 5.2 pounds. So, less likely to have that happen. Plus, look at the distribution. Got 5.5 here. And the value that's 7.5. 7.5. 5.5 here. If, so this is when n, or when it's in part A. Now part B, still have our mean of 7.5, still have 5.5, but our standard deviation is lower. That means we're more spread out. So 5.5, instead of being real close, it may be over here. And now there's just a little bit of shading. So the probability is going to go down. So you can read our answer. The probability that one baby is less than 5.5 pounds which is about 2 standard deviations below the mean. And the other probability is that then the mean of 3 babies weights are less than 5.5. So they're going to offset each other. They're going to average out. You may have one small baby, but you're not going to have 3 small babies. And in the second one, we're looking at the average, which will be closer to the mean. Really, it comes down to variability. Those of us who said the sample sizes were different. Letter A is not a sample. It is the population. 1 is not a sample. We got to be careful about that. So we'll talk about variability. Moving along. Number 6, last one. We're almost there. Find the probability that the weight of a randomly selected candy bar is less than 7.85 ounces. This problem was very good. The only problem I saw, we didn't write that. Or some of us didn't even write probability of x being less than or equal to 7.85. Then we get a 4 candy bar random sample. Center. Now when you say the center is 8.1, you have to say what kind of center it is. We have 3 measures of center. There is the mean, the median, and pretty much the useless mode, And if we're talking about symmetrical stuff, we don't want mode. We don't want median, we want mean. The mean is still 8.1. Standard deviation changes where we have sigma divided by the square root of n. 0.1 divided by the square root of 4, so 0.05. And it's normal because the normal, or the population, is normal, right up here. Or the sampling distribution of the mean is also normal, or approximately normal. I would say approximately, because we don't know if it's perfect, but that's what I would look at. So again, that was pretty good. Letter C was pretty good. Again, some of us did not do our distribution over here. We need to do that. Some of us told me 2.87 times 10 to whatever. That's fine. Some wrote it out. I don't even know how to do that. Something like that. One person, though, put equals 0. It does not equal 0. It is approximately 0. So it's about 0. But there's a big difference. There's a difference between very unlikely and impossible. And very likely still has a chance of happening. And stranger things have happened. Then letter D, would your answers to A, B, or C be affected if the weights of the chocolate bar produced by the machine were distinctly non-normal? Yes. Because if the population is not normal, the sampling distribution wouldn't be normal. So we couldn't do our norm CDF or normal CDF. We couldn't do any probabilities. Because all we know are normal probabilities. We'll get to talk to 2 more different types of distributions. But that's what we're looking for. Remember then, also, that we get to use a formula sheet on the exam. Remind me if I don't put them out originally, but I want to show us what is on that formula sheet. Head on over to our Google Classroom page. I'm not even going to edit that in. Keep it in there. First thing, actually, almost done here. If the computer wants to cooperate, that would be awesome. Maybe we can open this up. Ah, it's almost there. There we go. Oh, you've seen a lot of these formulas. The ones that we're using for this chapter, thought I could write on it. Apparently cannot. But it's here. Oh, actually here. Nope, I take it back. Mu of p hat equals p. Sigma of p hat equals the square root of p times 1 minus p over n. X bar is the mean of a random sample of size n from an infinite population with mean mu. Standard deviation is, or mean and standard deviation of this. But again, we need a 10% rule to do that. But that is our standard deviation. We saw that over and over again. And that's it. Just these couple things. Because then this stuff starts, well, really just this one line starts our next chapter. So if you still have any questions, you want to go over something else, please just email me, send me a message on the mine, or any other way you can communicate with me, and that would be fine.